Hi again from Ludovico Biagio of Politecnico di Milano. Today we start a following topic that comes in consequence of the previous ones, and it is related to multidimensional random variables. Up to now we have seen monodimensional random variables. X is a point in the real axis. Y as a function of x is again a monodimensional random variable. Now we are moving to the space of the two-dimensional random variables. Then clearly we will generalize to the n-dimensional random variable, but let's stay on the two-dimensional now. So the content of the next slot of presentation is the definition of a two-dimensional random variable. What is the joint density function between the two components of our random variable? What are their marginal distributions? What is the mean and the covariance of a random variables? And what are the propagation laws for a two-dimensional random variable? So let's start with the definition of a two-dimensional random variable. We have two monodimensional random variables, x and y, that are ruled defined on the same experiment capital omega. The properties of each one individual of these random variables are completely defined by giving their cumulative distribution of probability, so capital F of x and capital F of y. Their joint properties, I mean the probability that a point xy is in an arbitrary region D of the plane, cannot be generally determined only by knowing f of x and f of y. We need to define a joint cumulative distribution function. In particular, let's define fxy of xy, the probability of the event that is defined for each one xy belonging to R, multiplied by R, of the intersection of ax and ay, where that is the set of omega such that x of omega is smaller than x and y of omega is smaller than y. You see the graphical representation here. You have the x-axis, you have the y-axis. In the blue-gray region is depicted the region. On x and y you have two given values, x and y, you see on the axis. The blue region depicts the region in which x is smaller than the given x. The purple region depicts the region in which y is smaller than the given y. The intersection of the two regions is the region in which x is smaller than given x and y is smaller than given y. So, let's see what is the probability to have the random variable x comprised in the interval x plus delta x, the random variable y comprised in the interval y plus delta y. It is a rectangle, and this is exactly pictured in this slide. So you have f of x plus delta x, y plus delta a. You have to subtract f xy of y x plus delta x. Sorry, I inverted y and x. You have to subtract f of x y plus delta y, and because you have subtracted two times the same quantity, you have to add f of xy, exactly in the formula written below the graph. In case the two random variables x and y are continuous, we can introduce the definition of the joint density function. The joint density function is computed taking the cumulative distribution function fx way by deriving it 2 times with respect to x and with respect to y, exactly as it is written in this formula. Therefore, we can compute the probability that x way are in an arbitrary region D of the plane by the simple integration. The probability of x way belong to D is the double integral in the x and the y of the joint density function fx way. Moreover, given the joint density function of a two-dimensional random variable, we can compute from it the joint cumulative distribution function by integration. Capital F of x way will be the integral from minus infinite to x of the integral from minus infinite to y of the density function integrated in the x the y. Last properties, quite intuitive, are that the integral between minus infinite and plus infinite in x and minus infinite and plus infinity in y of the density function of x way is equal to 1. That follows from the fact that capital X smaller or equal to infinite and capital Y smaller or equal to infinite is clearly the certain event. Now, given a two-dimensional random variable, the individual distribution or probability of each one of them, so the individual of x and the individual of y, are called marginal distribution. In particular, we can define these quantities. The marginal cumulative distribution of x, capital F, is equal to the limit for y that tends to plus infinite of x way, or of the joint cumulative distribution of x and y. Correspondingly, the cumulative marginal distribution of y, capital F y, is defined as the limit for x that tends to plus infinite of the joint cumulative distribution fx way. The density marginal function of x on the right of the slide is the integral between minus infinite and plus infinite of the density joint function of x way integrated over dy. Correspondingly, the density function of y is defined as the integral between minus infinite and plus infinite of the joint density function fxy integrated, in this case, on dx. Now, let's suppose we have... Now, let's make a step on the case of discrete random variable. Now, let's suppose that you have a two-dimensional random variable composed by an x and y component that is of a discrete type. So we have values, discrete values, xe and ye, and for each one couple of xe, yj, we can define a joint probability as the probability that capital X is equal to xe, capital Y is equal to yj. This is the joint probability ej, to summarize the symbolism. Now the marginal probability function, in this case, can be expressed in terms of joint probability of x and y. So we have that the probability of x equal to e is equal to the sum over j of all the pej. You take all the possible values of j, you compute the sum of the probability of ej, and you obtain something that is function only of xe. On the contrary, if you want to compute the marginal probability function for y, you have that pj is equal to the sum of pej over, in this case, all the possible values xe and their probability. Finally, note that, exactly as in the continuous case, the sum over E of PE is the sum over E of the sum over J of PEJ, and this is clearly equal to 1. And the same can be said for the sum over J of PJ. That is the sum of the joint probabilities over all the possible couples of values, that clearly is equal again to 1. Let's go back now to the definition of independent events in probability general theory, and let's look how this idea, this concept, propagates for random variables. If you remember, two events A and B are said to be independent when the probability of the intersection of A and B is equal to the probability of A that multiplies the probability of B. This is the general idea of independence. Now let's generalize to random variables. So we have x and y. We define the two different events, x smaller than a given value and y smaller than another given value. Let's suppose we define that they are independent. This means, in practice, that the joint probability, the probability of the intersection, x smaller or equal to the given value for x and y smaller or equal to the given value for y, must be equal to the marginal probability x smaller than the given value for x multiplied by p of y smaller than the given value for y. This clearly yields to the following conditions. The joint cumulative distribution of xy is the product of the marginal cumulative distribution of x multiplied by the marginal cumulative distribution of y. The joint density of xy is equal to the product of the marginal density for x that multiplies the marginal density for y. Clearly, for discrete random variables, where the probability is a pointwise function, the probability of a joint value of xe and yj is equal to the probability of x equal e that multiplies the probability of y equal j. Now, exactly as we did for the monodimensional random variables, we go to the computation and the definition of the mean and the covariance of a two-dimensional random variables. In general, we can extend what we have said for monodimensional variables. The properties of two random variables are completely specified when we know their joint distribution. But again, for certain specific application, for certain practical computation, we can just work with a subset of important parameters. Let's suppose we have a function g of xy that maps the random variables xy in a new variable z. Clearly, z is a random variable whose domain is, again, capital omega. That is the domain of x, that is the domain of y. We want to express, in a general formulation, the mean of the random variable z in terms of the joint density of x and y, fxy. The theorem that can be proved, we are not going to prove, but it is quite simple and it is quite intuitive, is that the expectation of z that can be defined as the expectation of g of xy is exactly the integral between minus infinite and plus infinite in the x of the integral between minus infinite and plus infinite in the way of gx way that multiplies the joint density function of x way. In case x and y are discrete, the formula, the integration, as usual, reduces to a sum, and we can write that the expectation, the mean of z, that is again the expectation of g of x way, is the sum over all the possible outcomes of x, they are numbered e, and all the possible outcomes of way, that is numbered by j, of gxe way j, that multiplies the probability of ej. Now, what happens if you have several z obtained as a mapping of x way? For example, z1 equal to g1 of x way, z2 equal g2 of x way, up to zn equal gn of x way. You could ask, you could wonder, what happens if you want to map the mean of x way into the sum z1 plus z2 plus ... zn. Strictly speaking, you have to compute the expectation of g1 plus g2 plus etc up to gn, but the expectation for the continuous case is an integral, for the discrete case is a sum. The sum and the integral are linear operators, and so the expectation of z1 plus z2 etc up to zn is simply given by the expectation of g1 plus the expectation of g2 plus up to the sum of expectation of gn. Now, let's go a little bit deeper into details about the idea of mean and covariance for a two-dimensional random variable. What is the mean, given a random variable x way, what is the mean of x, the individual mean of x? It is the expectation in the x-way space of x, and strictly speaking it can be computed by the integral between minus infinite and plus infinite in the x of the integral of minus infinite to plus infinite in the way of the product x that multiplies the joint density function of x way. This clearly can be written in a slightly different way. The integral of between minus infinite and plus infinite of x in dx that multiplies the integral between minus infinite and plus infinite of x way in the way. But the second integral is that what we have defined, the marginal density function of x, so the mean of x can be written as the integral between minus infinite and plus infinite of x that multiplies its marginal density function in the x. Exactly the same can be done for mu way. Mu way is the integral between minus infinite and plus infinite of way that multiplies the marginal density function of way in the way. So the mean for the random variable x way in two dimension is a point in the plane, and we can write that the expectation of x way is a two-dimensional vector whose first component is mu x and the second component is mu way. What about the variance of x and y? Let's start with the definition of the variance of x. The definition is the standard one, is the expectation of x minus mu x squared. To compute this quantity, we need a double integral between minus infinite and plus infinite in the x the way of x minus mu x squared that multiplies the joint density function fxy. But this can be written as the integral in the x of x minus mu x squared that multiplies the integral in the way of fxy between minus infinite and plus infinite. This is clearly the integral between minus infinite and plus infinite in the x of x minus mu x squared that multiplies the marginal density function of x. For the variance of y, we can repeat exactly the same reasoning, and we have that it is the integral in the way, in this case, of y minus mu y squared that multiplies the marginal density function of y. Now we introduce a new quantity, the covariance of two random variables, or if you prefer, the covariance of the two components of a two-dimensional random variable. The name usually used is sigma xy, and from a symbolic point of view, it is defined as the expectation value of x minus mu x that multiplies y minus mu y. From a numerical point of view, it can be computed as the double integral over the x and the y from minus infinite to plus infinite of x minus mu x, y minus mu y multiplied by the joint density distribution. This can be written also by unpacking the two brackets as the double integral from minus infinite to plus infinite of xy that multiplies the joint density function of xy in the x and the y minus the product mu x mu y. Or, if you want, it is the expectation of xy minus the expectation of x that multiplies the expectation of y. Finally, we can define a very important quantity that is the covariance matrix of xy. The covariance matrix for a two-dimensional variable xy, indeed, is a matrix of 2 by 2, and it is defined as the expectation value of the vector x minus mu x, y minus mu y, that multiplies its transpose, so x minus mu x, y minus mu y transpose. So, in the first diagonal element, you have x minus mu x squared. In the second diagonal element, you have the y minus mu y squared. In the off-diagonal elements, you have x minus mu x that multiplies y minus mu y in both the two elements. And so, given the above definition of variance and covariance, the covariance matrix contains in the first diagonal element the variance of x, in the second diagonal element the variance of y, and off diagonals you have the covariance of x and y. The covariance matrix of x, y is clearly symmetric because sigma xy is equal to sigma y x. This is quite easy to prove, a little bit more difficult, but it is a fundamental property of covariance matrices. It is positive definite. What does it mean, positive definite? Take any vector belonging to R2, lambda 1, lambda 2. The positive definiteness is that lambda transpose that multiplies C that multiplies lambda. It is a quadratic form, the result is a scalar, and it is always greater than 0. Finally, before stepping to the next topic, we can define the correlation coefficient between the two components of a two-dimensional random variable, x and y, and it is given by the ratio between the covariance between x and y and the square roots of the individual variances. So the square root of the variance of x that multiplies the square root of the variance of y. This ratio is called correlation coefficient, and it can be quite easily proved that the correlation coefficient is always comprised between -1 and 1. In particular, and this is very easy to be proved, when y is linearly dependent from x, I mean y equal to ax plus b, the correlation coefficient is equal to +1 or -1 consistently to the sign of a. +1 if a is positive, -1 if a is negative. When the correlation coefficient is 0, x and y are said to be uncorrelated. Okay, let's see what happens about statistical independence. There is a fundamental theorem that states that if x and y are statistically independent, they are uncorrelated. In fact, what does it mean that they are statistically independent? It means that the joint density function is equal to the product of the individual density functions or the marginal density functions. But this means that the expectation of xy, that is exactly the expectation of xy, is equal to the product of the expectation of x that multiplies the expectation of y. So the covariance is generally given by the expectation of the product xy minus the product of the expectation of x multiplied by the expectation of y. We have said that the expectation of xy is the expectation of x that multiplies expectation of y in this particular case. So sigma xy is 0. So sigma xy over sigma x that multiplies sigma y, it is 0. It doesn't hold the vice versa. If two variables are uncorrelated, you cannot state that they are also independent. This holds only for variables that are normally distributed. If you have x and y that are normally distributed and they are uncorrelated, that means the correlation coefficient is 0, so they are also statistically independent. But this holds only for normal distributions. Clearly, an important consequence is that when x and y are independent or are uncorrelated, the covariance matrix is diagonal. On the contrary, if the covariance matrix is diagonal, you cannot say that they are independent unless they are normally distributed. Now, this slot of slides will go to the last topic of this lecture, that is the propagation laws for two-dimensional variables. So, what is the problem? Given two random variables x and y, given two functions g of xy and h of xy, we can build the two new random variables v, namely g of xy, and w, namely h of xy. These functions are agate composite functions of the domain of capital omega, that is, they are still random variables. We would like to find the joint distribution of v and w by starting with the joint distribution of x and y. But this is not so tricky as a problem to be solved, and in this set of introduction to statistics, we are going just to find out the propagation of the mean and of the covariance in terms of the mean and covariance of x, y. Okay, let's start with the easiest case, that is that of linear transformations. I mean that V is a linear transformation of X way and W is a linear transformation of X way again. So, from a matricial point of view, this relation can be written as follows. You have a vector VW. This vector is equal to a certain matrix A that multiplies the vector X way plus a vector B. If you want to be more explicit, the A matrix contains 4 terms, named A11, A12, A21, A22. In particular, so V will be equal to A11x plus A12y plus B1, and W will be equal to A21x plus A22y plus B2. How the mean propagates? It is very simple. It is a generalization of the monodimensional case. You have that the mu of the resulting vector, that is the mu of V mu of W, is the matrix A applied to the mu of X mu of Y plus B, or in a compact notation, A mu of XY plus B. The covariance matrix of the two-dimensional variable VW can be proved to be equal to the matrix A that multiplies the covariance matrix of XY that multiplies the transpose of A. In case of a linear transformation between one two-dimensional variable to another two-dimensional variable, we can also strictly compute the density, the joint density function of VW. It is given by the joint density function of XY for X equal to the inverse of A that multiplies VW minus B over the determinant of A. Now, what happens when the function g and h are not linear? Exactly as in the monodimensional case, we can make a linearization of g and h around the mean value of x and the mean value of y. So we have that we can write VW equal to respectively g evaluated in mu x mu y and h evaluated in mu x mu y plus the so-called Jacobian of the transformation evaluated in the mean of xy that multiplies x minus mu x, y minus mu y. The Jacobian is a matrix whose components are the partial derivatives of the functions of transformations with respect to the two variables from which we are starting. So, in the first diagonal element, you will have the derivative of g with respect to x. In the second column on the first row, you will have the derivative of g with respect to y. So the first line contains in some way the linearization for v. In the second row, you have the derivative of h with respect to x, and finally the derivative of h with respect to y. All these derivatives evaluated in the mean value of x and y. So, the propagation formula becomes, by linearization, as follows. The mu of v and the mu of w are almost equal to the g function evaluated in mu x mu y and to the h function evaluated in mu x mu y. The covariance matrix of the new variable vw will be given by the Jacobian of the function of the transformation that multiplies the covariance matrix of xy that multiplies the transpose of the Jacobian. You see that in some way if you look back to the monodimensional case, we are finding exactly the same properties. Here we have vectors, matrices, there we have scalars and simple derivatives. So this discussion ends the first part about two-dimensional random variables. We will have a second part that is related to the conditional distribution and conditional expected values. Now, as usual, for this slot, some question time in order to understand, to let you understand if you are well confident. The first question is, write the joint density function of a two-dimensional random variable whose components are independent, and in particular they are standardized normal random variables. So you have Z, you have the two components of Z. Z1 is the normal distribution with zero mean and variance equal to 1, and the same also for Z2. Then consider a two-dimensional random variable X, so I mean X way, X equal to a certain matrix that multiplies Z plus B. A clearly is 2 by 2. The determinant of A must be different from 0. You have to find, by propagation, the mean and the covariance matrix of X. Moreover, write the joint density function of X, knowing that the marginal, it is given by this formula that I don't need to read, and that the determinant of A that multiplies A transpose, remember, it is the square of the determinant of A. Then, given a two-dimensional continuous random variable, discrete, write the relation between the joint density function, or the probability, because it is a discrete variable, and the marginal density or probability of its component. Consider the following singular two-dimensional random variable, x composed by x equal to omega and y equal to a omega plus b. Compute the mean and the covariance matrix of x, compute the determinant of cxx. Sketch the set of all the possible x way value and compute then the linear correlation coefficient. Now you have few exercises that are related to the transformation between two-dimensional random variable that you can solve.